Alright, still at a hotel. It's pretty noisy, so we're just going to fight through it because this is a pretty short exercise. Because essentially all we need to do is figure out a way to apply exercise 1.5.6 and we're good. So let Fm, we're going to break each of these Fm's up into the positive part and the negative part. Why am I using m's when I could use n's? Okay, we'll see how far I get before I switch back. Okay. And let f plus be simply the sum from n equals 0 to infinity of fn plus, and similarly fn minus is going to be the sum from n equals 0 to infinity of fn minus. And of course, fn plus and fn minus are both functions which are greater than or equal to 0. So fn plus is the positive part and fn minus is the negative part. Okay, now since fn plus and fn minus are both greater than or equal to 0, we know by exercise 1.5.6 that the integral of the sum from n equals 0 to infinity of fn, and then this could be a plus or a minus d mu, we could just bring out the sum. That's exactly what that exercise was all about. You end up just using monotone convergence. It's not too difficult. Also, we need to use this fact that the sum of the integrals of the absolute values of the fn's is finite. So we have infinity is greater than this sum from n equals 0 to infinity, the integral of the norm of fn d mu. This is precisely, well, we can break this up. Well, the absolute value is precisely the positive part plus the negative part, just by the definitions of the positive and negative parts. And now we're taking a finite sum here, so this is going to be the sum from n equals 0 to infinity, and this integral can be broken up into two. We have integral of fn plus the integral of fn minus. And so now we're taking an infinite sum of these finite sums, and so we can rearrange this sum pretty much however we want. So this ends up just being the integral of fn plus d mu, that whole thing plus this whole thing, n equals 0 to infinity fn minus d mu. Okay, so so this is what we wanted to prove, because this tells us that each of these sums is finite, and that's why we need this condition. We need this sum to be finite because thus this tells us that the sum from n equals 0 to infinity of the integral of fn plus d mu minus the sum from n equals 0 to infinity the integral of fn minus d mu is defined. Because if both of these were infinity, then we couldn't do the subtraction. The subtraction would be undefined. But since both of these things are finite, we can subtract them and everything works out fine. And in fact, I think this is really too much. I don't think we need this thing to be finite. I think we need to have either this first sum is finite or the second sum is finite. And once you have that, the theorem should still hold. Sorry about the plane. Actually, I'm not sorry because it's not something I have control over. So we need this to be defined. And in order for it to be defined, we only need one of these things to be finite. Although maybe the reason that they didn't include that as part of the condition is that if they stated the condition as either this sum is finite or this sum is finite, then it's clear what you have to do. It's clear that you have to take the function and break it into the positive and negative parts if the condition involves both the positive and negative parts. But anyways, so we can take the sum from I did it. I used m instead. It should be n equals 0 to infinity. integral of Fn d mu equals the sum, then Fn, integral of Fn plus minus the integral of Fn minus, no, minus just this, d mu. So now we can break this up, n equals 0 to infinity, move that a little bit, sorry about that. Okay, so integral of Fn plus d mu minus integral of Fn minus d mu. Now we can break this up. Integral sum n equals 0 to infinity, integral Fn plus d mu minus sum n equals 0 to infinity, integral of Fn minus d mu. Wait. No. Wait, what? What am I trying to do? I'm trying to move the sums inside. And I can do that now because these are positive functions. So we can move the sums inside. Minus the integral sum from n equals 0 to infinity, Fn minus d mu. And now this is a finite thing, so we can this is just sum n equals 0 to infinity, Fn plus d mu, minus, and now we just basically work backwards. Fn minus d mu, no d mu's, the d mu should be on the outside. So then this is just the sum from n equals 0 to infinity, just rearranging these, Fn plus minus Fn minus d mu. And then this is precisely integral sum n equals 0 to infinity Fn d mu. And that's what we wanted to prove. And so we're done. So like I said, I don't think that this is the strongest form of this statement. I think that the conditions can be slightly weaker and it will still hold. But in any case, this works out, and yeah, all we had to do was just check that this subtraction was well defined, and as soon as it was, it just ends up being just apply exercise 1.5.6, and you're good. So that's all we have to do, and so we're done with the exercise.